Imagine looking up at the night sky and seeing billions of stars scattered across the darkness. Each point of light represents a massive sun, perhaps with planets orbiting around it, all held together by invisible forces that stretch across unimaginable distances. Now imagine zooming in closer, past the planets, past the atoms that make up everything around us, deeper and deeper, until we reach the smallest building blocks of reality itself. What would we find there? For centuries, scientists have been on a quest to understand the fundamental forces that govern our universe. We live in a cosmos where gravity keeps our feet planted on the ground and holds the planets in their orbits around the sun. Electricity powers our devices and creates the lightning that illuminates storm clouds. Deep within the nuclei of atoms, powerful forces bind particles together, while other forces cause them to decay and transform. These forces seem completely different from each other. Gravity works across vast cosmic distances, keeping galaxies from flying apart. Electromagnetic forces create the light we see and the magnetic fields that protect our planet. Nuclear forces operate only within the tiny confines of atomic nuclei, invisible to our everyday experience. Each force appears to follow its own rules, operate in its own domain, and behave according to its own mysterious logic. But what if this apparent separation is just an illusion? What if, beneath the surface complexity of our universe, there exists a single, elegant explanation that connects all these forces together? What if the same fundamental principle that governs the smallest particle also determines the motion of the largest galaxy? This is the dream that has captivated physicists for generations. They call it the theory of everything, a single framework that would unite all the forces of nature under one comprehensive understanding. It would be the ultimate achievement in science, the final piece of the puzzle that explains how our universe truly works. Tonight, we embark on a journey to explore one of the most ambitious attempts to find this unified theory. It's called string theory, and it proposes something almost magical. Instead of thinking of the fundamental building blocks of reality as tiny points with no size or structure, string theory suggests that everything in the universe, from the electrons in our bodies to the photons that carry light, is made of incredibly small, vibrating strings. These strings are so tiny that if an atom were the size of our solar system, a string would still be smaller than a tree on Earth. Yet according to this theory, the different ways these strings vibrate determine whether they become the particles that make up matter or the forces that act upon that matter. A string vibrating in one pattern might become an electron. The same string vibrating in a different pattern might become a particle of light, or even contribute to the force of gravity itself. If string theory is correct, then the incredible diversity we see in our universe, from the gentle pull of gravity to the explosive power of nuclear reactions, all emerges from the same fundamental source. The theory suggests that what we perceive as completely different phenomena are actually just different melodies played by the same cosmic strings, each vibration creating its own unique contribution to the symphony of existence. The implications are staggering. String theory doesn't just promise to explain the forces we already know about. It suggests that our familiar three-dimensional world of length, width, and height, plus the dimension of time, might be only a small part of a much larger reality. The theory predicts the existence of additional dimensions, curled up so small that we cannot perceive them, yet essential to the way our universe operates. But string theory is more than just an abstract mathematical exercise. If it proves to be correct, it could revolutionize our understanding of reality itself. It might explain mysteries that have puzzled scientists for decades, like why gravity is so much weaker than the other forces, or what happened in the first moments after the Big Bang. It could provide insights into the nature of black holes, the possibility of parallel universes, and the ultimate fate of everything that exists. Yet string theory also presents us with profound challenges. The mathematics involved is extraordinarily complex, requiring concepts that push the boundaries of human understanding. The scales at which strings operate are so small that we may never be able to observe them directly with any conceivable technology. Testing the theory requires us to think in new ways about what it means to verify scientific truth. As we begin this exploration, we find ourselves at the frontier of human knowledge, peering into concepts that challenge our most basic assumptions about reality. We will discover how string theory emerged from the creative minds of brilliant physicists, how it attempts to bridge the gap between the quantum world of the very small and the relativistic world of the very large, and why it continues to captivate researchers despite its many unsolved puzzles. This is not just a story about physics or mathematics. It's a story about humanity's deepest desire to understand our place in the cosmos, to find meaning and connection in what might otherwise seem like a chaotic and incomprehensible universe. String theory represents one of our most ambitious attempts to glimpse the mind of creation itself, to understand the fundamental code that writes the story of everything that was, is, and ever will be. Whether string theory ultimately proves to be the theory of everything, or simply another stepping stone on our journey toward truth, it has already transformed the way we think about reality. It has opened new pathways of thought, inspired new questions, and reminded us that the universe is far stranger and more wonderful than we ever imagined. So let us begin this journey together, following the vibrating strings that might hold the key to understanding everything. To understand why string theory represents such a revolutionary idea, we must first explore the four fundamental forces that govern every interaction in our universe. These forces are the invisible architects of reality, shaping everything from the structure of atoms to the formation of galaxies. Each force has its own personality, its own domain of influence, and its own way of making its presence known. Let us begin with gravity, perhaps the most familiar force in our daily experience. Every morning when you wake up, gravity pulls you toward the earth, keeping you anchored to your bed rather than floating toward the ceiling. When you drop a coffee cup, gravity guides its inevitable journey to the floor. When you look up at the moon, you are seeing the result of gravity's gentle embrace, holding our celestial companion in its eternal dance around Earth. But gravity is far more than just the force that keeps our feet on the ground. It is the cosmic sculptor that shapes the largest structures in the universe. Gravity pulls together vast clouds of gas and dust to form stars, then binds those stars into galaxies containing hundreds of billions of individual suns. It creates the invisible scaffolding upon which the entire universe hangs, determining the paths of planets, the life cycles of stars, and the ultimate fate of everything that exists. What makes gravity truly remarkable is its incredible reach. Unlike other forces that weaken rapidly with distance, gravity extends its influence across billions of light years, connecting every particle of matter to every other particle in the universe. The gravity of distant stars tugs gently on your body right now, though the effect is far too small for you to notice. In this sense, we are all connected to the cosmos through the invisible threads of gravitational attraction. Yet for all its cosmic importance, gravity is actually the weakest of the four fundamental forces. This might seem surprising until you consider that it takes the entire mass of our planet to keep you from floating away, while a small magnet can easily overcome Earth's gravitational pull on a paperclip. This weakness of gravity compared to other forces is one of the great mysteries that string theory hopes to explain. The second fundamental force is electromagnetism, the source of light, electricity, and magnetism. Every time you flip a light switch, turn on your phone, or use any electronic device, you are harnessing the power of electromagnetic forces. These forces govern the behavior of charged particles like electrons and protons, creating the electrical currents that power our modern world. Electromagnetism is responsible for the structure of atoms themselves. The negatively charged electrons that orbit atomic nuclei are held in place by electromagnetic attraction to the positively charged protons at the atom's center. This same force creates the chemical bonds that link atoms together to form molecules, making possible everything from water and air to the complex proteins that enable life. Light itself is an electromagnetic phenomenon, consisting of waves of electric and magnetic fields rippling through space. When you see the colors of a rainbow, you are witnessing different frequencies of electromagnetic radiation, each one carrying its own unique energy signature. Radio waves, microwaves, Infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays are all different manifestations of the same electromagnetic force, distinguished only by their frequency and energy. Unlike gravity, which only attracts, electromagnetism can both attract and repel. Opposite charges attract each other, while like charges push apart. This dual nature allows electromagnetic forces to create stable structures, while also providing the dynamic interactions necessary for change and complexity. The delicate balance between attraction and repulsion in electromagnetic forces is what makes chemistry possible, allowing atoms to bond in countless different arrangements to create the rich diversity of materials we see around us. The third fundamental force operates in a realm largely hidden from our everyday experience, yet it is responsible for the very existence of matter as we know it. This is the strong nuclear force, sometimes called the strong force, which binds protons and neutrons together in atomic nuclei. Without this force, atoms could not exist, and the universe would be nothing but a thin soup of isolated particles drifting through empty space. The strong force is incredibly powerful, far stronger than either gravity or electromagnetism, but it operates only across extremely short distances. Within the confines of an atomic nucleus, which measures only about 1/10,000th the width of an atom, the strong force overwhelms all other influences. It must be extraordinarily powerful because it faces a formidable challenge, holding positively charged protons together despite their electromagnetic repulsion. Think about this remarkable feat. Protons carry positive electric charge, and like charges, repel each other with tremendous force when squeezed into the tiny volume of a nucleus. The electromagnetic force tries desperately to blow the nucleus apart, yet the strong force holds it together with even greater strength. This is why atomic nuclei are so stable, and why it takes enormous amounts of energy to break them apart or force them together. The strong force is also responsible for binding quarks together to form protons and neutrons. Quarks are the fundamental building blocks of these nuclear particles, and they are held together by the strong force in a way that is unlike any other interaction in nature. The more you try to pull quarks apart, the stronger the force becomes, like trying to stretch a rubber band that gets progressively stiffer. This property ensures that quarks are never found in isolation, but always remain bound together in groups. The fourth and final fundamental force is the weak nuclear force, which governs certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the Sun and other stars. Despite its name, the weak force is not actually weak compared to gravity. It is only weak compared to the strong nuclear force and electromagnetism. The weak force is responsible for transforming one type of particle into another through processes that change the very identity of atomic nuclei. When a neutron decays into a proton, electron, and neutrino, it is the weak force that orchestrates this transformation. When nuclear fusion occurs in the core of the Sun, converting hydrogen into helium and releasing the light and heat that sustain life on Earth, the weak force plays an essential role in making these reactions possible. Unlike the other forces, the weak force does not simply push or pull particles around. Instead, it changes their fundamental nature, converting quarks from one type to another and enabling particles to transmute into entirely different species. This transformative power makes the weak force essential for the nuclear processes that create the heavier elements in stars and distribute them throughout the universe when those stars explode as supernovae. Each of these four forces operates according to its own set of rules and principles. Gravity follows the curved geometry of space-time described by Einstein's general relativity. Electromagnetism obeys the equations discovered by Maxwell in the 19th century and later refined by quantum mechanics. The strong and weak nuclear forces are governed by the complex mathematics of quantum field theory, involving concepts like gauge symmetries and spontaneous symmetry breaking. For most of the 20th century, physicists developed separate theories to describe each force. These theories are remarkably successful within their own domains. General relativity accurately predicts the behavior of gravity from the smallest asteroids to the largest galaxy clusters. Quantum electrodynamics describes electromagnetic phenomena with incredible precision. Quantum chromodynamics explains the strong force, while the electroweak theory unifies electromagnetism and the weak force at high energies. Yet despite their individual successes, these theories remain frustratingly separate. They use different mathematical frameworks, operate on different scales, and seem to describe completely different aspects of reality. Gravity is described by the smooth, continuous geometry of curved space-time, while the other three forces are understood through the discrete, probabilistic world of quantum mechanics. This separation creates profound problems when physicists try to understand situations where multiple forces become important simultaneously. What happens at the center of a black hole where gravity becomes so strong that quantum effects cannot be ignored? How did the universe behave in the first moments after the Big Bang, when all four forces may have been unified into a single superforce? What is the quantum nature of gravity itself? These questions cannot be answered by our current separate theories. They require a new framework that can describe all four forces as different aspects of a single, underlying reality. They demand a theory that can bridge the gap between the quantum world of particles and forces and the geometric world of curved space-time. This is the challenge that string theory attempts to meet. Rather than treating the four forces as separate phenomena requiring separate explanations, string theory proposes that they are all different manifestations of the same fundamental reality. According to this revolutionary idea, gravity, electromagnetism, the strong force, and the weak force all emerge from the vibrations of tiny, one-dimensional strings that exist at the most basic level of physical reality. If string theory is correct, then the apparent diversity of forces in our universe is like the apparent diversity of sounds produced by a violin. Just as a single violin string can produce many different notes depending on how it vibrates, the fundamental strings of reality can produce all the different forces and particles we observe, each one corresponding to a different vibrational pattern. This elegant unification would represent the ultimate triumph of human understanding, revealing that beneath the complex tapestry of physical phenomena lies a single, beautiful principle. But to appreciate why string theory offers such promise, we must first understand why the unification of forces has proven so difficult, and why our current theories, despite their individual successes, are ultimately incomplete. Imagine trying to understand a conversation where two people are speaking completely different languages. Each person makes perfect sense within their own linguistic framework, but when they try to communicate with each other, confusion and misunderstanding arise. This is remarkably similar to the situation that has confronted physicists for nearly a century as they attempt to reconcile two of the most successful theories in the history of science, general relativity and quantum mechanics. General relativity, Einstein's masterpiece completed in 1915, revolutionized our understanding of gravity, space, and time. According to this theory, what we experience as gravity is not actually a force in the traditional sense, but rather the curvature of space-time itself. Massive objects like stars and planets warp the fabric of space-time around them, creating curved paths that other objects follow. When Earth orbits the Sun, it is not being pulled by a mysterious gravitational force, but rather following the straightest possible path through curved space-time. This geometric view of gravity has proven to be extraordinarily accurate. General relativity predicted that massive objects would bend light, that time would run slower in strong gravitational fields, and that accelerating masses would create ripples in space-time called gravitational waves. All of these predictions have been confirmed by precise experiments and observations. The global positioning system in your smartphone requires corrections based on general relativity to maintain accuracy. The detection of gravitational waves by laser interferometry has opened an entirely new window for observing the universe. General relativity describes a universe that is smooth, continuous, and deterministic. Space-time forms a seamless fabric that can be curved and twisted, but never torn or broken. If you know the exact configuration of matter and energy at any given moment, Einstein's equations can, in principle, predict the evolution of the entire universe for all future time. This is a universe of elegant mathematical curves and precise geometric relationships, where every event follows inevitably from the conditions that preceded it. But step into the quantum mechanical world, and you enter a realm that operates by completely different rules. Quantum mechanics, developed primarily in the 1920s and 30s, describes the behavior of atoms, electrons, photons, and other fundamental particles. In this microscopic domain, the smooth certainties of general relativity dissolve into a fog of probability and uncertainty. According to quantum mechanics, Particles do not have definite positions and velocities until they are observed. Instead, they exist in a state of superposition, occupying multiple possible states simultaneously until measurement forces them to choose one specific outcome. An electron orbiting an atom does not follow a definite path like a planet orbiting the sun. Instead, it exists as a cloud of probability, more likely to be found in some regions than others, but never precisely localized until someone looks for it. The quantum world is inherently probabilistic. Even if you know everything possible about a quantum system, you cannot predict with certainty what will happen when you measure it. You can only calculate the probabilities of different outcomes. This fundamental randomness is not due to our ignorance or the limitations of our measuring instruments. It appears to be a basic feature of reality itself at the smallest scales. Quantum mechanics also reveals that the vacuum of empty space is far from empty. What appears to be perfectly empty space is actually seething with activity, filled with virtual particles that pop into existence and vanish again in incredibly brief intervals. These quantum fluctuations create a fundamental graininess to space and time at the smallest scales, suggesting that the smooth fabric of space-time, described by general relativity, might be an approximation that breaks down when examined too closely. The mathematical frameworks of these two theories could hardly be more different. General relativity is built on the foundation of differential geometry, describing curved surfaces and the paths of objects moving through them. Its equations are deterministic, predicting exactly how space-time will evolve given any initial configuration of matter and energy. Quantum mechanics, on the other hand, is built on linear algebra and probability theory, describing wave functions that evolve according to the Schrödinger equation and collapse unpredictably when measurements are made. For most practical purposes, this division works well. General relativity accurately describes the behavior of large objects like planets, stars, and galaxies, where quantum effects are negligible. Quantum mechanics successfully explains the behavior of atoms, molecules, and subatomic particles, where gravitational effects are far too weak to matter. The two theories operate in different domains, like two separate kingdoms that rarely interact. But there are situations where both theories should apply simultaneously, and in these cases, the incompatibility becomes a serious problem. Consider what happens at the center of a black hole, where matter is compressed to infinite density according to general relativity. Surely quantum effects must become important under such extreme conditions, but we have no way to combine the two theories to understand what actually occurs. Or consider the first moments after the Big Bang, when the entire observable universe was compressed into a volume smaller than an atomic nucleus. During this epoch, gravitational effects were enormously strong because of the incredible density of matter and energy, but quantum effects were equally important because everything was confined to such a tiny space. To understand the birth of our universe, we need a theory that can handle both quantum mechanics and gravity simultaneously. The problem runs even deeper than these exotic scenarios. According to quantum mechanics, all forces should be mediated by particles. The electromagnetic force is carried by photons, the weak nuclear force by W and Z bosons, and the strong nuclear force by gluons. But what about gravity? If gravity is to be incorporated into the quantum mechanical framework, it should also be mediated by particles, presumably called gravitons. However, when physicists attempt to apply the standard techniques of quantum mechanics to gravity, they encounter mathematical disasters. The equations produce infinite answers to physically meaningful questions, a sure sign that something is fundamentally wrong with the approach. Unlike the other forces, gravity seems to resist quantization, refusing to fit into the quantum mechanical framework that works so well for electromagnetism and the nuclear forces. This problem is not merely technical, but strikes at the heart of our understanding of reality. If quantum mechanics is truly universal, applying to all physical phenomena, then gravity must have a quantum description. But if general relativity correctly describes gravity as the curvature of space-time, then how can this geometric property be quantized? How can the smooth fabric of space-time be made compatible with the discrete, probabilistic nature of quantum mechanics? The incompatibility between general relativity and quantum mechanics also raises profound questions about the nature of space and time themselves. General relativity treats space and time as a continuous, smooth background upon which physical events unfold. But quantum mechanics suggests that at the smallest scales, this smooth background dissolves into quantum foam, a chaotic froth of virtual particles and fluctuating fields. If space and time are truly quantized at the smallest scales, then they are not the smooth, continuous entities described by general relativity. Instead, they might be made up of discrete units, like pixels on a computer screen that appear smooth when viewed from a distance, but reveal their granular nature when examined closely. This would mean that our familiar concepts of space and time are emergent properties that arise from some more fundamental level of reality. The search for a quantum theory of gravity has occupied some of the brightest minds in physics for decades. Various approaches have been tried, from loop quantum gravity, which attempts to quantize space-time directly, to emergent gravity theories, which suggest that gravity might not be fundamental, but rather an emergent property of more basic quantum phenomena. But perhaps the most ambitious approach is string theory, which attempts to resolve the conflict between general relativity and quantum mechanics in a completely different way. Instead of trying to quantize gravity or geometrize quantum mechanics, string theory suggests that both are approximations of a more fundamental reality involving vibrating strings in higher dimensional space. According to string theory, the apparent incompatibility between general relativity and quantum mechanics arises because we have been thinking about the problem in the wrong way. We have been trying to force two different languages to communicate with each other, when what we really need is a new language that encompasses both. String theory proposes to be that new language, providing a single framework that naturally incorporates both the geometric insights of general relativity and the quantum mechanical behavior of fundamental particles. If string theory is correct, then the smooth spacetime of general relativity and the discrete particles of quantum mechanics are both emergent properties of vibrating strings. Gravity emerges from certain vibrational patterns of closed strings, while the particles that make up matter and mediate the other forces emerge from different vibrational patterns. The apparent conflict between the two theories dissolves because they are both describing different aspects of the same underlying string dynamics. But string theory demands a price for this unification. It requires us to abandon our familiar three-dimensional conception of space and accept the existence of additional dimensions that we cannot directly perceive. It forces us to think about particles not as points but as extended objects with their own internal structure. It challenges our most basic intuitions about the nature of reality and pushes the boundaries of mathematical complexity far beyond what previous theories have required. The need for such a radical new approach becomes clear when we consider the limitations of our current understanding. Despite the tremendous success of both general relativity and quantum mechanics within their respective domains, neither theory is complete. General relativity cannot explain what happens at the quantum level, while quantum mechanics cannot incorporate gravity. Both theories have internal inconsistencies and unanswered questions that suggest they are approximations of some deeper truth. The development of a unified theory that combines general relativity and quantum mechanics would represent one of the greatest intellectual achievements in human history. It would provide a single, coherent description of all known physical phenomena, from the behavior of subatomic particles to the evolution of the entire universe. It would answer fundamental questions about the nature of space, time, matter, and energy that have puzzled humanity for millennia. More than that, a unified theory would likely reveal new phenomena and new possibilities that we cannot currently imagine. Just as quantum mechanics led to the development of lasers, transistors, and computers, and general relativity enabled GPS navigation and gravitational wave detection, a theory that unifies all the forces of nature would undoubtedly open up new technologies and new ways of understanding our place in the cosmos. This is the promise that string theory offers: a single, elegant framework that can describe everything from the smallest vibrations of quantum strings to the largest structures in the universe. But to understand how string theory attempts to fulfill this promise, we must delve deeper into its revolutionary proposals about the fundamental nature of reality itself. The year was 1968, and a young Italian physicist named Gabriele Veneziano was struggling with one of the most perplexing problems in particle physics. He was trying to understand the strong nuclear force, the mysterious interaction that holds protons and neutrons together inside atomic nuclei. The mathematics was incredibly complex, and the experimental data seemed to defy every theoretical approach that physicists had tried. Veneziano was working late one evening in his office, surrounded by pages of calculations and half-empty coffee cups, when he remembered something from his graduate studies. There was an obscure mathematical formula discovered centuries earlier by the Swiss mathematician Leonhard Euler, a formula that described certain geometric relationships but had no known application to physics. On a whim, Veneziano decided to see if this ancient mathematical curiosity might somehow relate to the behavior of strongly interacting particles. What happened next was one of those magical moments in science when pure mathematical beauty reveals a hidden truth about the physical world. Euler's formula fit the experimental data with stunning accuracy. But even more remarkable was what the mathematics was telling him about the nature of the particles themselves. According to the equations, the fundamental constituents of matter were not point-like particles, as everyone had assumed, but rather tiny, vibrating strings. This was the birth of string theory, though Veneziano himself did not immediately realize the full implications of his discovery. He had stumbled upon an entirely new way of thinking about the fundamental building blocks of reality, one that would eventually grow into humanity's most ambitious attempt to understand the deepest laws of nature. The idea seemed almost absurd at first. How could particles, which had always been conceived as dimensionless points with no internal structure, actually be tiny strings? The strings that Veneziano's mathematics described were unimaginably small, far smaller than anything that could ever be observed directly. If you could somehow magnify a proton until it was the size of our solar system, one of these fundamental strings would still be no larger than a typical tree on Earth. But the mathematical elegance was undeniable. When Veneziano and other physicists began to explore the implications of string theory more deeply, they discovered that these tiny vibrating strings could account for all the different types of particles that had been discovered in high-energy experiments. Just as a violin string can produce different musical notes depending on how it vibrates, a fundamental string could become different particles depending on its vibrational pattern. A string vibrating in one particular mode might manifest as an electron, with its characteristic mass and electric charge. The same string vibrating in a different pattern might become a photon, the particle that carries electromagnetic force. Another vibrational pattern might produce a quark, one of the building blocks of protons and neutrons. The entire zoo of subatomic particles that had been discovered throughout the 20th century could potentially be understood as different harmonics of the same fundamental strings. This was a profound shift in perspective. Instead of thinking of the universe as composed of many different types of fundamental particles, each with its own unique properties and behaviors, string theory suggested that there might be only one type of truly fundamental object, the string itself. All the apparent diversity of particles would then be like the apparent diversity of sounds that can be produced by a single musical instrument. Leonard Susskind, one of the founding fathers of string theory, was among the first to recognize the revolutionary implications of Veneziano's discovery. Working at Stanford University in the early 1970s, Susskind began to develop the physical interpretation of the mathematical formalism that Veneziano had uncovered. He realized that if particles were really strings, then the theory would have to be fundamentally different from any previous approach to physics. In traditional particle physics, interactions between particles are thought of as collisions between point-like objects. When two particles come together, they might bounce off each other, exchange energy and momentum, or transform into different types of particles. These interactions can be represented by diagrams that show particles as lines meeting at specific points in space and time. But if particles are actually strings, then their interactions must be understood very differently. When two strings interact, they do not simply collide at a point. Instead, they can join together to form a single string, or a single string can split apart to form two separate strings. These processes occur smoothly and continuously, without the sharp discontinuities that characterize point-particle interactions. Imagine two pieces of rope floating through space and gradually approaching each other. As they get closer, their ends might touch and fuse together, creating a single longer piece of rope. Or consider a single piece of rope that develops a weak spot and gradually tears apart into two separate pieces. String interactions are similar to these processes, but occurring in the quantum mechanical realm, where the ropes are unimaginably tiny and their behavior is governed by probability rather than certainty. This smooth, continuous nature of string interactions was one of the first hints that string theory might solve some of the mathematical problems that had plagued previous attempts to unify the forces of nature. In point particle theories, calculations often produce infinite results when physicists try to account for all possible quantum mechanical effects. These infinities are a sign that something is fundamentally wrong with the theoretical approach, like dividing by zero in a mathematical equation. But in string theory, the extended nature of strings naturally smooths out these infinities. Instead of interactions occurring at specific points, which can lead to mathematical singularities, string interactions are spread out over the finite size of the strings themselves. This built-in smoothness eliminates many of the mathematical pathologies that had made it impossible to create a consistent quantum theory of gravity. The early pioneers of string theory soon discovered that their new framework had even more surprising properties. Michael Green and John Schwartz, working in the 1980s, found that string theory was not just a theory of the strong nuclear force, as Veneziano had originally intended. Under certain conditions, the theory naturally incorporated gravity as well, arising from specific vibrational patterns of closed strings that formed complete loops rather than having free ends. This was an unexpected bonus. No one had set out to create a quantum theory of gravity, but string theory seemed to produce one automatically. The gravitational force emerged from the mathematics without being put in by hand, suggesting that string theory might indeed be the long-sought unified theory that could describe all the forces of nature within a single framework. But string theory also made demands that seemed to push the boundaries of physical possibility. The mathematics worked consistently only if the strings existed in more than the familiar 3 dimensions of space plus 1 dimension of time. Depending on the specific version of string theory, the strings needed to vibrate in 9, 10, or even 11-dimensional space-time to maintain mathematical consistency. This requirement for extra dimensions was initially seen as a fatal flaw in the theory. After all, we clearly live in a world with only 3 spatial dimensions: length, width, and height. How could a theory that required 6 or 7 additional dimensions have any relevance to the real universe? The answer, physicists realized, might lie in the concept of compactification. Just as a 3-dimensional garden hose appears one-dimensional when viewed from a great distance, the extra dimensions required by string theory might be curled up so tightly that they are imperceptible at the scales we can observe. These compactified dimensions would still be there, influencing the behavior of strings and determining the properties of the particles we observe, but they would be hidden from direct detection. Kaluza and Klein had proposed a similar idea decades earlier in their attempt to unify gravity and electromagnetism, but string theory gave new life and mathematical precision to the concept of hidden dimensions. The particular way in which the extra dimensions are compactified would determine the specific properties of particles and forces in our observable 3-dimensional world. As string theory developed throughout the 1970s and 80s, it attracted some of the most brilliant theoretical physicists in the world. Edward Witten at the Institute for Advanced Study, Joel Scherk in France, and many others contributed crucial insights that helped transform Veneziano's original mathematical curiosity into a comprehensive framework for understanding fundamental physics. The theory evolved and branched into different versions, each with its own mathematical structure and physical predictions. There was Type 1 string theory, which involved open strings with free ends. Type II and Type IIB theories described closed strings in different mathematical settings. Heterotic string theories combined aspects of different approaches to create hybrid frameworks with unique properties. Each version of string theory seemed to describe a different possible universe, with different particles, different forces, and different physical laws. This multiplicity was both exciting and troubling. On one hand, it suggested that string theory was rich enough to accommodate many different physical possibilities. On the other hand, it raised the question of which version, if any, described our actual universe. The mathematical complexity of string theory also presented unprecedented challenges. The equations involved concepts from some of the most advanced areas of mathematics, including algebraic topology, differential geometry, and representation theory. Understanding string theory required physicists to become mathematicians, and the mathematical techniques needed to make progress in the theory often had to be invented from scratch. Despite these challenges, The early results were encouraging enough to attract significant attention from the physics community. String theory seemed to offer solutions to problems that had stymied physicists for decades. It provided a finite, mathematically consistent approach to quantum gravity. It suggested natural explanations for the existence of multiple forces and particles. It hinted at deep connections between apparently unrelated areas of mathematics and physics. But string theory also faced growing skepticism from some quarters. Critics pointed out that the theory made very few testable predictions about the real world. The energy scales at which stringy effects would become apparent were so enormous that no conceivable experiment could reach them. The number of possible ways to compactify the extra dimensions was vast, potentially leading to an almost infinite number of different possible universes. Nevertheless, research in string theory continued to accelerate throughout the 1980s. The theory had acquired a momentum of its own, driven by its mathematical beauty and its promise of ultimate unification. Even if experimental tests were not immediately possible, the theoretical insights were profound enough to justify continued investigation. The stage was set for what would become known as the first superstring revolution, a period of rapid progress that would transform string theory from a curious mathematical framework into a serious candidate for the theory of everything. The revolution would bring new understanding of the relationship between different versions of string theory, reveal unexpected connections to other areas of physics and mathematics, and establish string theory as one of the most important theoretical developments in modern science. But first, physicists needed to grapple with one of string theory's most radical implications: the existence of dimensions beyond the familiar three of space and one of time. Understanding these hidden dimensions would prove to be crucial for unlocking the full potential of string theory as a unified description of all the forces of nature. Take a moment to look around the room where you are right now. You can move forward and backward, left and right, up and down. These three directions define the space in which we live our daily lives, the familiar dimensions of length, width, and height that have shaped human understanding of reality since ancient times. Add to this the dimension of time, which carries us inexorably from past to future, and you have the four-dimensional space-time that Einstein showed us more than a century ago. For most people, this four-dimensional reality seems not just complete, but obvious. After all, we can see and touch objects in three-dimensional space, and we experience the passage of time with every heartbeat and every breath. What could be more real than the world of our direct experience? Yet string theory tells us that this familiar reality is just a shadow of something far grander and more complex. A universe with additional dimensions curled up so small and hidden so deeply that they remain invisible to our senses. This idea is not entirely new to physics. In 1919, a little-known German mathematician named Theodor Kaluza wrote to Albert Einstein with a remarkable proposal. What if the familiar three dimensions of space were not the whole story? What if there was a fourth spatial dimension, hidden from our perception, that could help explain the mysterious relationship between gravity and electromagnetism? Kaluza's idea was brilliant in its simplicity. Einstein had shown that gravity could be understood as the curvature of four-dimensional spacetime. Kaluza proposed extending this insight to 5 dimensions, with the 5th dimension somehow connected to electromagnetic forces. In this 5-dimensional world, gravity and electromagnetism would be unified as different aspects of the same geometric phenomenon. A few years later, the Swedish physicist Oskar Klein refined Kaluza's proposal by suggesting that the extra dimension might be compactified, rolled up into a tiny circle so small that we cannot detect it. Imagine an ant walking on a tightrope stretched between 2 buildings. From a distance, the tightrope appears to be one-dimensional, just a line through space. But if you could shrink yourself down to the size of the ant, you would discover that the tightrope actually has a second dimension, the circular dimension around its circumference. The ant can move not just along the rope but also around it, following paths that are invisible to distant observers. Klein proposed that our universe might be similar to this tightrope. What appears to be 3-dimensional space might actually have additional dimensions curled up so tightly that they are imperceptible at the scales of everyday experience. These compactified dimensions would still exist and would still influence physical phenomena, but they would be hidden from direct observation. The Kaluza-Klein theory was mathematically elegant. but it faced serious problems when confronted with experimental reality. The unification of gravity and electromagnetism that it promised did not match the observed properties of these forces. The theory made predictions about particle masses and interaction strengths that disagreed with measurements. By the middle of the 20th century, most physicists had abandoned the idea of extra dimensions as an interesting mathematical curiosity that had little relevance to the real world. But string theory brought the concept of extra dimensions roaring back to life with new urgency and mathematical precision. Unlike the Kaluza-Klein theory, which introduced extra dimensions as a convenience to unify known forces, string theory demanded extra dimensions for its very mathematical consistency. The equations simply did not work in the familiar 4 dimensions of space-time. They required additional dimensions to avoid mathematical contradictions and infinite results. The reason for this requirement lies in the fundamental nature of string vibrations. A point particle, having no spatial extent, can vibrate in any number of dimensions without mathematical inconsistency. But a string, being an extended object, has internal structure that constrains how it can move and vibrate. Just as a guitar string can only produce harmonious music if its tension, length, and material properties are carefully matched, the fundamental strings of string theory can only exist in harmony if the dimensions of space-time have exactly the right number and properties. The specific number of dimensions required depends on which version of string theory you are considering. The original bosonic string theory required 26 dimensions for mathematical consistency. Superstring theories, which incorporate a symmetry between matter particles and force-carrying particles, work in 10 dimensions. M-theory, which attempts to unify different versions of string theory, operates in 11 dimensions. In every case, the number of dimensions is fixed by the mathematics, not chosen for convenience or aesthetic appeal. This means that string theory makes a definite, testable prediction about the structure of reality. If the theory is correct, then our universe must have more dimensions than the 4 we directly observe. The extra dimensions must be real, physical aspects of space-time, not just mathematical artifacts or useful calculational tricks. But why don't we notice these extra dimensions? If they really exist, why has no one ever stepped sideways into a 5th dimension, or fallen upward into a 6th? The answer, according to string theory, is that the extra dimensions are compactified on scales so incredibly small that they are beyond the reach of any technology we can imagine. To understand what this means, consider the analogy of a sheet of paper viewed from different distances. From across a room, the paper appears to be 2-dimensional, having only length and width. Move closer, and you can see that it actually has a 3rd dimension, thickness, but this dimension is much smaller than the other 2. Now imagine shrinking the thickness of the paper smaller and smaller, while keeping its length and width the same. Eventually, the thickness would become so small that even with the most powerful microscope, the paper would appear to be perfectly 2-dimensional. String theory suggests that something similar has happened to the extra dimensions of space. They exist at every point in the familiar 3-dimensional space we observe, but they are curled up so tightly that their size is comparable to the Planck length, about 10 to the minus 33 centimeters. This is so small that if you could somehow magnify a single atom until it was the size of the entire observable universe, the compactified dimensions would still be smaller than the original atom. At such scales, the very concepts of space and measurement begin to break down. The compactified dimensions exist in a realm where quantum mechanical uncertainty becomes dominant, where the smooth geometry of Einstein's relativity gives way to the probabilistic foam of quantum fluctuations. Yet these hidden dimensions are not just empty space rolled up into tiny balls. They have complex geometric structures that determine the physics we observe in our familiar 3-dimensional world. The shape and size of the compactified dimensions act like a hidden control panel for the universe, determining which particles can exist, how strongly they interact with each other, and what forces operate between them. Different compactification schemes lead to different possible universes with different physical laws. Some might have more or fewer types of particles. Others might have forces with different strengths or different ranges. Still, others might be completely lifeless, lacking the delicate balance of properties necessary for the formation of atoms, molecules, and complex structures. This connection between the geometry of extra dimensions and the physics of our observable universe is one of the most profound insights of string theory. It suggests that the apparent fundamental constants of nature, quantities like the mass of the electron or the strength of the electromagnetic force, are not truly fundamental at all. Instead, they are determined by the geometric properties of dimensions we cannot see. To visualize this relationship, imagine a three-dimensional object casting a two-dimensional shadow on a wall. The shape of the shadow depends on both the shape of the object and the angle from which light strikes it. Similarly, the physics we observe in our three-dimensional world might be the shadow cast by higher dimensional geometry. Just as rotating the three-dimensional object changes the shape of its shadow, changing the geometry of the compactified dimensions would change the physical laws we observe. This insight has profound implications for our understanding of why the universe appears to be fine-tuned for the existence of life. The masses of particles, the strengths of forces, and the values of physical constants all seem to be precisely calibrated to allow the formation of atoms, stars, planets, and eventually living beings. Even tiny changes in these values would make the universe either collapse immediately after the Big Bang or expand so rapidly that no structures could ever form. String theory suggests that this apparent fine-tuning might not be a coincidence or evidence of divine intervention, but rather a consequence of the particular way the extra dimensions happen to be compactified in our region of the universe. Other regions might have different compactification schemes, leading to different physical laws and different possibilities for structure and complexity. But the compactified dimensions of string theory are not static, unchanging geometric objects. They can evolve and change over time, potentially leading to changes in the apparent constants of nature. The dimensions can also vibrate and oscillate, creating new types of particles and forces that have no analog in our familiar four-dimensional experience. Some of these extra-dimensional vibrations might be detectable, at least in principle, by sufficiently sensitive experiments. High-energy particle collisions might occasionally probe deeply enough into the structure of space-time to reveal the existence of compactified dimensions. Gravitational experiments might detect tiny deviations from the inverse square law that would indicate the presence of extra dimensions. Cosmological observations might reveal signatures of extra-dimensional physics in the cosmic microwave background or the large-scale structure of the universe. The search for experimental evidence of extra dimensions has become one of the most active areas of research in modern physics. Particle accelerators like the Large Hadron Collider are designed to reach energies high enough to potentially detect extra-dimensional effects. Gravitational wave detectors might be sensitive enough to observe the subtle modifications to gravity that would result from the existence of compactified dimensions. But even if direct detection remains beyond our current capabilities, the mathematical consistency of string theory provides strong, indirect evidence that extra dimensions must exist. The theory works so well at solving long-standing problems in theoretical physics that many researchers are convinced the extra dimensions must be real, even if they remain hidden from our direct observation. The existence of extra dimensions also opens up extraordinary possibilities for the future of physics and technology. If we could ever learn to access or manipulate the compactified dimensions, we might gain control over the fundamental constants of nature themselves. We might be able to create regions of space with different physical laws, or develop technologies that seem like magic from our current perspective. More immediately, understanding the geometry of extra dimensions might help us solve some of the deepest mysteries in cosmology and particle physics. Why is gravity so much weaker than the other forces? What is the nature of dark matter and dark energy? How did the universe begin, and what will be its ultimate fate? The answers to these questions might be written in the hidden dimensions that surround us at every moment. Dimensions that exist in the very space between the atoms of our bodies, yet remain as remote and inaccessible as the most distant galaxies. String theory has transformed our conception of space from a simple, empty stage upon which physical events unfold into a rich, complex, multidimensional arena where the geometry itself plays an active role in determining the laws of physics. The familiar three dimensions of our daily experience are just the visible surface of a reality that extends into realms we are only beginning to imagine and understand. Imagine holding a guitar in your hands and plucking a single string. That one string, depending on how you touch it, where you press it, and how you set it vibrating, can produce an enormous variety of sounds. press it at different positions along its length, and you create different pitches. Pluck it gently or strike it hard, and you change the volume and timbre. Add harmonics and overtones, and you can create sounds ranging from pure, bell-like tones to rich, complex chords that seem to contain entire musical worlds within them. Now imagine that this single guitar string is not just producing different sounds, but actually becoming different objects entirely. When it vibrates in one pattern, it transforms into a note of music. When it vibrates in another pattern, it becomes a beam of light. Change the vibration again, and it becomes a piece of matter, complete with mass and electric charge. This might seem like pure fantasy, but it captures the essential insight of string theory, that all the fundamental particles and forces in our universe might be different vibrational states of the same underlying strings. In string theory, these fundamental strings come in two basic varieties, each with its own unique properties and possibilities. The distinction between them is surprisingly simple yet profound in its implications for the structure of reality itself. The first type is called an open string, and as the name suggests, it has two free ends, like a piece of rope or a guitar string stretched between two posts. You can imagine an open string as a tiny line segment floating through space, with each end free to move independently. The endpoints of an open string are special places where the string can interact with other objects in ways that the middle portions cannot. When an open string vibrates, it creates standing wave patterns along its length, much like the waves you see when you shake a jump rope up and down. These vibrational patterns determine what type of particle the string appears to be from our perspective. A string vibrating in its simplest mode, with just one wave along its length, might manifest as a photon, the particle that carries electromagnetic force. More complex vibrational patterns, with multiple waves and nodes along the string, correspond to particles with different masses, charges, and other properties. The free ends of open strings play a crucial role in determining how these strings can interact with each other and with other types of strings. When two open strings approach each other, their endpoints can touch and connect, allowing the strings to join together into a single longer string. Alternatively, a single open string can split apart at some point along its length, creating two separate open strings from what was originally one. These joining and splitting processes represent the fundamental interactions between particles in string theory. When a photon is absorbed by an electron, for example, string theory describes this as an open string representing the photon connecting with an open string representing the electron, creating a combined system that then evolves according to the laws of string dynamics. The second type of fundamental string is called a closed string, and it forms a complete loop with no free ends, like a rubber band or a circular piece of wire. Closed strings have a very different character from open strings because they have no special endpoints where interactions can occur. Instead, closed strings can only interact through processes where the entire loop comes into contact with other strings or breaks apart to form separate loops. The vibrational patterns of closed strings are also different from those of open strings. Instead of standing waves with fixed endpoints, closed strings support traveling waves that circulate around the loop. These circulating vibrations can move clockwise or counterclockwise around the string, and they can combine in complex ways to create a rich variety of possible vibrational states. One of the most significant discoveries in string theory was the realization that closed strings naturally give rise to gravitons, the hypothetical particles that carry the gravitational force. This emergence of gravity from closed string vibrations was not anticipated by the early developers of string theory, but it provided the first hint that string theory might be more than just a theory of nuclear forces. It suggested that string theory could be a unified description of all the forces in nature, including gravity. The mathematical relationship between open and closed strings is one of the most elegant aspects of string theory. Under certain conditions, open strings can join together at their endpoints to form closed strings. Imagine taking the two ends of a piece of rope and tying them together to form a loop. Similarly, closed strings can break apart to form pairs of open strings, like cutting a rubber band to create a straight piece of elastic. These transformations between open and closed strings represent processes where matter particles, represented by open strings, can create or destroy force-carrying particles, represented by closed strings. This provides a natural mechanism for the interactions between matter and forces that we observe in nature. But the relationship between different types of strings goes even deeper than this simple open-closed distinction. Within each category, strings can exist in many different vibrational states, each corresponding to a different type of particle with its own unique properties. Consider first the open strings. The simplest vibrational state of an open string corresponds to a massless particle, typically a photon or another force-carrying particle. As the vibrational patterns become more complex, with more waves and higher frequencies, the corresponding particles become more massive. The exact relationship between the vibrational frequency and the particle mass is determined by the fundamental properties of the strings themselves. Open strings can also carry electric charge, which arises from the way the string endpoints interact with background fields in the higher dimensional space where the strings live. Different charge configurations correspond to different types of particles. A string with no net charge might represent a photon or a neutrino. A string with positive charge could be a positron. A string with negative charge might be an electron. The vibrational patterns of open strings can also encode other particle properties, such as spin, which determines how particles behave when rotated in space. Low-frequency vibrations typically correspond to particles with low spin, while higher-frequency vibrations can produce particles with higher spin values. Closed strings exhibit an even richer variety of possible vibrational states because their loop geometry allows for more complex wave patterns. The waves traveling around a closed string can interfere with each other in constructive or destructive ways, creating intricate patterns of peaks and valleys that encode the properties of the resulting particles. The most important closed string vibrational state is the one that corresponds to the graviton, the particle that would carry gravitational force if gravity follows the same quantum mechanical rules as the other forces. The emergence of gravitons from closed string vibrations was one of the first major successes of string theory, providing a natural way to incorporate gravity into the quantum mechanical framework. But closed strings can produce much more than just gravitons. Different vibrational patterns can correspond to particles that carry the other fundamental forces, as well as various types of matter particles. Some closed string states might correspond to particles that do not exist in our familiar four-dimensional world, but would become important in the higher dimensional reality where strings actually live. The mathematical description of string vibrations involves concepts from some of the most advanced areas of physics and mathematics. The vibrational modes of strings are described by wave functions that must satisfy complex boundary conditions and symmetry requirements. These wave functions encode not just the energy and momentum of the resulting particles, but also their transformation properties under various symmetries of space-time. Understanding these mathematical structures has led to profound insights into the relationship between geometry and physics. The vibrational patterns of strings are intimately connected to the geometric properties of the higher dimensional spaces in which the strings move. Different geometric backgrounds can support different types of string vibrations, leading to different possible sets of particles and forces. This connection between geometry and particle physics suggests that the fundamental laws of nature might be consequences of the geometric structure of reality itself. The particles we observe and the forces that act between them might be reflections of the hidden geometric relationships that exist in the extra dimensions of string theory. The study of string vibrations has also revealed unexpected connections between apparently unrelated areas of physics. Vibrational patterns that arise in string theory have been found to be relevant to condensed matter physics, where they help explain the behavior of electrons in certain materials. They have applications in nuclear physics, where they provide new insights into the structure of atomic nuclei. They even have relevance to cosmology, where string vibrational states might help explain the mysterious dark matter and dark energy that dominate our universe. Perhaps most remarkably, the mathematical framework developed to understand string vibrations has found applications far beyond physics. The same mathematical tools are used in pure mathematics to study abstract geometric objects and topological spaces. They have applications in computer science, where they help optimize complex algorithms. They even have relevance to biology, where similar mathematical structures arise in the study of protein folding and genetic networks. This unexpected breadth of applications suggests that string theory has uncovered something fundamental about the mathematical structure of reality itself. The vibrational patterns of strings might represent a kind of universal language that describes not just the particles and forces of physics, but many other complex systems in nature and mathematics. Yet for all their mathematical elegance and broad applicability, the vibrational states of strings remain largely theoretical constructs. The energies required to directly observe individual string vibrations are far beyond anything achievable with current or foreseeable technology. We can study their mathematical properties and explore their theoretical implications, but we cannot yet point to a specific particle in nature and say with certainty that it is a particular vibrational state of a fundamental string. This gap between mathematical theory and experimental reality is one of the ongoing challenges facing string theory. While the mathematical framework is incredibly rich and suggests deep insights into the nature of reality, translating these insights into testable predictions about the world we observe remains an enormous challenge. Nevertheless, the study of string vibrations continues to yield new insights and unexpected connections. Each new mathematical development opens up new possibilities for understanding how the complex world we observe might emerge from the simple vibrations of fundamental strings. Whether these strings are real physical objects or mathematical abstractions that capture some deeper truth about reality, they have already transformed our understanding of the relationship between mathematics and physics, between geometry and particle interactions, and between the simple and the complex in the natural world. Picture a magnificent symphony orchestra preparing for a performance. On the stage you see violins, cellos, trumpets, flutes, drums, and dozens of other instruments, each with its own unique voice and character. To an untrained observer, these instruments might seem completely different from each other, each following its own musical logic and producing its own distinctive sounds. But a skilled conductor knows that beneath this apparent diversity lies a deeper unity. All these different instruments are variations on the same fundamental theme. They create music by causing air molecules to vibrate in organized patterns. This analogy captures one of the most profound promises of string theory. Just as different musical instruments are all variations on the theme of controlled vibration, string theory suggests that the four fundamental forces of nature, which appear so different from our everyday perspective, are actually different manifestations of the same underlying phenomenon: the vibration of fundamental strings in higher dimensional space. Throughout the history of physics, the dream of unification has driven many of the greatest discoveries. When Isaac Newton realized that the same force that causes an apple to fall from a tree also keeps the planets in their orbits around the sun, he unified terrestrial and celestial mechanics under the single principle of universal gravitation. When James Clerk Maxwell showed that electricity and magnetism are two aspects of the same electromagnetic field, he revealed a hidden unity that had previously been invisible. Einstein spent the last 30 years of his life searching for a unified field theory that would connect gravity and electromagnetism in a single mathematical framework. Though he never succeeded, his quest inspired generations of physicists to continue the search for ever deeper levels of unification. The development of the Standard Model of particle physics in the latter half of the 20th century achieved a partial unification by showing that the electromagnetic force and the weak nuclear force are actually two aspects of a single, electro-weak force at high energies. But gravity remains stubbornly separate from the other forces, refusing to fit into the quantum mechanical framework that successfully described electromagnetism and the nuclear forces. Every attempt to quantize gravity led to mathematical inconsistencies and infinite results that seem to indicate a fundamental incompatibility between general relativity and quantum mechanics. String theory promises to resolve this ancient conflict by providing a framework in which all four forces arise naturally from the same source. According to string theory, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force are all different vibrational patterns of the same fundamental strings. This would represent the ultimate unification, reducing all the apparent complexity of physical forces to variations on a single, elegant theme. To understand how this unification works, we must first examine how each force emerges from string vibrations. Let us begin with electromagnetism, the force that governs the behavior of electrically charged particles and gives rise to all electrical and magnetic phenomena. In string theory, electromagnetic forces arise from specific vibrational patterns of open strings. When an open string vibrates in its lowest energy mode, it creates a massless particle with the properties we associate with photons. the particles that carry electromagnetic force. These string vibrations naturally incorporate all the features that make electromagnetism unique: the ability to both attract and repel, the infinite range of the force, and the precise mathematical relationships described by Maxwell's equations. What makes this emergence of electromagnetism particularly elegant is that it requires no special assumptions or additional ingredients beyond the basic framework of string theory. The mathematical consistency of the theory automatically ensures that the electromagnetic force has exactly the right properties to match experimental observations. The charge of particles, the strength of electromagnetic interactions, and the speed of light all emerge as natural consequences of the string vibrational patterns. The weak nuclear force, which governs certain types of radioactive decay and plays a crucial role in nuclear fusion reactions, also emerges from open string vibrations, but in a more subtle way. The particles that carry the weak force, known as W and Z bosons, correspond to higher energy vibrational modes of open strings. These particles are much more massive than photons, which explains why the weak force has a much shorter range than electromagnetism. String theory naturally incorporates the unification of electromagnetic and weak forces that was discovered in the 1970s. At high energies, when the mass difference between photons and W and Z bosons becomes less important, the electromagnetic and weak forces merge into a single electroweak force. This unification emerges automatically from the string theory framework, without requiring the complex mathematical machinery that was needed to achieve it in conventional particle physics. The strong nuclear force, which binds quarks together to form protons and neutrons, and holds atomic nuclei together against electromagnetic repulsion, also finds a natural home in string theory. The particles that carry the strong force, called gluons, correspond to specific vibrational patterns of open strings. But the strong force has some unusual properties that make it quite different from electromagnetism and the weak force. Unlike photons, which can travel freely through space, gluons are always confined within the particles they bind together. You can never isolate a single gluon or observe it traveling freely through space. This property, known as confinement, emerges naturally from the way open strings interact in string theory. The mathematical structure that gives rise to gluon vibrations automatically ensures that they remain bound within composite particles. String theory also explains another peculiar property of the strong force: asymptotic freedom. At very short distances or very high energies, the strong force actually becomes weaker, not stronger. This counterintuitive behavior, which was discovered experimentally in the 1970s, emerges naturally from the string theory description of gluon interactions. But perhaps the most remarkable achievement of string theory is its natural incorporation of gravity into the same framework that describes the other forces. In conventional quantum field theory, gravity is described by Einstein's general relativity, which treats space-time as a smooth, curved manifold. This geometric description seems fundamentally incompatible with the particle-based description of the other forces. String theory resolves this apparent incompatibility by showing that gravity emerges from the vibrational patterns of closed strings. When a closed string vibrates in its lowest energy mode, it creates a massless particle with exactly the properties required for a graviton, the hypothetical quantum particle that would carry gravitational force. This emergence of gravity from closed string vibrations was one of the first major triumphs of string theory. Unlike the other forces, which had to be carefully constructed to match experimental observations, gravity appeared automatically in the theory without being explicitly put in. The mathematical consistency of string theory seemed to demand the existence of gravitational interactions. Moreover, the string theory description of gravity naturally avoids the mathematical infinities that plague conventional attempts to quantize general relativity. The extended nature of strings, rather than point-like particles, smooths out the sharp singularities that cause problems in point-particle theories. This suggests that string theory might finally provide the long-sought quantum theory of gravity that has eluded physicists for decades. The unification achieved by string theory goes beyond simply showing that all forces arise from string vibrations. The theory also reveals deep mathematical relationships between apparently different types of forces and particles. These relationships, known as dualities, show that what appears to be different physics in one description might actually be the same physics viewed from a different mathematical perspective. One of the most important dualities in string theory is the relationship between strongly coupled and weakly coupled regimes of the same theory. When the interactions between strings are very strong, making calculations extremely difficult, there often exists a dual description where the interactions are weak and calculations become manageable. This duality allows physicists to study aspects of string theory that would otherwise be mathematically intractable. Another remarkable duality relates gravity in higher dimensional space to quantum field theories without gravity in lower dimensional space. This correspondence, known as the ADS-CFT correspondence, suggests that gravitational physics in the bulk of a higher dimensional space is equivalent to non-gravitational physics on the boundary of that space. This duality has provided new insights into both quantum gravity and strongly interacting quantum field theories. These dualities hint at an even deeper level of unification than the simple emergence of all forces from string vibrations. They suggest that the different forces and particles we observe might be different faces of a single underlying mathematical structure, like different projections of a higher dimensional object onto lower dimensional surfaces. The mathematical framework that describes this unified structure is extraordinarily rich and complex. It involves concepts from some of the most advanced areas of mathematics, including algebraic geometry, differential topology, and representation theory. Understanding this mathematics requires physicists to develop new mathematical tools and techniques, often pushing the boundaries of human mathematical knowledge. But the rewards of this mathematical complexity are potentially enormous. If string theory is correct, it would provide humanity with the most complete description of physical reality ever achieved. It would explain not only how the forces of nature work, but why they have the particular strengths and properties that we observe. It would reveal the deep mathematical principles that govern everything from the behavior of subatomic particles to the evolution of the entire universe. The unification promised by string theory also has profound implications for our understanding of the relationship between mathematics and physics. The theory suggests that the fundamental laws of nature are not arbitrary rules imposed on a passive universe, but rather expressions of deep mathematical truths that exist independently of human observation. In this view, mathematics is not just a tool for describing nature, but the very language in which nature is written. Yet despite its mathematical elegance and theoretical promise, the unification achieved by string theory remains largely unverified by experiment. The energy scales at which the unified nature of the forces becomes apparent are far beyond anything achievable with current technology. We can study the mathematical structure of the theory and explore its theoretical implications, but we cannot yet perform experiments that directly confirm its predictions about the unification of forces. This gap between theoretical promise and experimental verification is one of the ongoing challenges facing string theory. While the mathematical unification is remarkably elegant and suggests deep insights into the nature of reality, translating these insights into testable predictions about the world we observe remains an enormous challenge. Nevertheless, the vision of unification that string theory provides continues to inspire physicists around the world. The idea that all the apparent complexity and diversity of physical phenomena might emerge from the simple vibrations of fundamental strings represents one of the most ambitious and beautiful ideas in the history of human thought. Whether this vision ultimately proves to be correct or not, it has already transformed our understanding of the relationship between the forces of nature and pointed the way toward new possibilities for understanding the deepest levels of physical reality. Imagine trying to study the behavior of dolphins by observing them from the surface of the ocean. You might catch glimpses of them when they leap above the water, see the ripples they create as they swim beneath the surface, or hear the sounds they make echoing through the waves. But most of their lives remain hidden in the depths, invisible to your direct observation. To truly understand dolphins, you would need to dive deep beneath the surface, into an alien underwater world where your normal senses and tools might not work as expected. String theory presents physicists with a similar challenge. The fundamental strings that supposedly make up all matter and forces in the universe exist at scales so incredibly small that they remain forever hidden beneath the surface of what we can directly observe. Unlike dolphins, which occasionally breach the surface where we can see them, Strings operate in a realm so remote from everyday experience that they may never reveal themselves through direct observation. This inaccessibility is not a minor technical problem that might be solved with better instruments or more sensitive detectors. It is a fundamental barrier that arises from the enormous difference between the scale at which strings operate and the scale at which we can perform experiments. The gap is so vast that it challenges our very conception of what it means to test a scientific theory. To appreciate the magnitude of this challenge, consider the size of a fundamental string according to string theory. These objects are believed to exist at the Planck scale, a realm where the familiar concepts of space and time begin to break down due to quantum mechanical effects. A typical string is thought to be about 10 to the minus 33 centimeters in length. This is not just small, it is unimaginably, incomprehensibly small. If you could somehow magnify an atom until it was the size of our entire solar system, a fundamental string would still be smaller than the period at the end of this sentence. If you could magnify a proton until it filled the entire observable universe, a string would still be no larger than a tree on Earth. These comparisons fail to capture the true scale of the problem, because human language and intuition simply have no adequate way to express such extreme differences in size. The energy required to directly probe the structure of strings is equally staggering. According to the principles of quantum mechanics, to observe objects at very small scales, you need particles with very high energies. The relationship is inverse. The smaller the scale you want to probe, the higher the energy required. To directly observe the vibrations of fundamental strings, you would need particle energies approaching the Planck energy, which is about 10 to the 19th billion electron volts. To put this in perspective, the most powerful particle accelerator ever built, the Large Hadron Collider, can accelerate particles to energies of about 10 trillion electron volts. This represents the absolute cutting edge of human technology, requiring a circular tunnel 27 kilometers in circumference and consuming enough electricity to power a small city. Yet even this magnificent machine falls short of the Planck energy by a factor of about 10 million. Building a particle accelerator capable of reaching Planck-scale energies would require resources far beyond anything imaginable with current or foreseeable technology. The accelerator would need to be larger than our solar system, possibly larger than our galaxy. The energy requirements would exceed the total power output of the Sun. Even if humanity somehow developed the technology and resources for such a project, the accelerator itself would likely collapse into a black hole long before it could perform any useful experiments. This seemingly insurmountable experimental challenge has led to intense debates within the physics community about the scientific status of string theory. Science has traditionally been based on the cycle of theoretical prediction, followed by experimental verification. A theory proposes that certain phenomena should occur under specific conditions. Experiments are designed to test these predictions, and the theory is accepted, modified, or rejected based on the experimental results. String theory appears to break this traditional cycle because its most fundamental predictions cannot be tested directly. Critics argue that a theory that cannot be experimentally verified is not really science, but rather philosophy or mathematics dressed up in the language of physics. They contend that without the possibility of experimental refutation, string theory cannot be subjected to the rigorous testing that distinguishes science from other forms of human inquiry. The mathematical complexity of string theory presents another formidable challenge that goes beyond the problems of experimental verification. Understanding string theory requires mastery of some of the most advanced mathematical concepts ever developed, involving areas of mathematics that most physicists have never encountered in their training. The theory draws on algebraic topology, differential geometry, complex analysis, representation theory, and many other specialized mathematical fields. This mathematical complexity means that only a relatively small number of researchers worldwide have the technical expertise necessary to work meaningfully in string theory. Even among those who do have the required mathematical background, calculations in string theory are often so complex that they can take months or years to complete, and the results are frequently so abstract that their physical interpretation remains unclear. The mathematical machinery of string theory also tends to generate an enormous number of possible solutions, each corresponding to a different way that the extra dimensions could be compactified, and each leading to a different set of physical laws in our observable four-dimensional world. Early estimates suggested that there might be tens of thousands of possible string theory vacua, each representing a different possible universe with its own unique properties. More recent work has suggested that the number of possibilities is far larger than originally thought. Some researchers now estimate that string theory might allow for 10 to the 500th different possible universes, a number so large that it exceeds the total number of atoms in the observable universe by an almost incomprehensible margin. This vast landscape of possibilities is both a blessing and a curse for string theory. On one hand, this enormous diversity suggests that string theory is rich enough to accommodate almost any conceivable set of physical laws. If our universe is indeed described by string theory, then somewhere in this vast landscape of possibilities, there should be a solution that matches our observed reality. The theory is so flexible that it seems capable of explaining almost anything we might discover about the fundamental nature of reality. On the other hand, this very flexibility raises serious questions about the predictive power of string theory. If the theory can accommodate almost any possible set of physical laws, then how can it be tested? What possible experimental result could falsify string theory if it can be made consistent with virtually any observation? Critics argue that a theory that can explain everything explains nothing, because it provides no basis for distinguishing between what should happen and what should not happen. The landscape of string theory solutions also raises profound questions about the uniqueness of physical laws. For most of the history of physics, researchers have assumed that there is one correct theory that describes our universe, and that this theory would make unique predictions about the values of fundamental constants and the properties of particles and forces. String theory suggests that this assumption might be wrong. If string theory is correct, then there might be no unique set of physical laws. Instead, different regions of a vast multiverse might be governed by different laws, corresponding to different solutions in the string theory landscape. Our particular universe would be just one possibility among an almost infinite number of alternatives, with no special status or fundamental reason for its particular properties. This possibility has led some string theorists to embrace what is known as the anthropic principle. According to this reasoning, we observe the particular physical laws that govern our universe not because they are uniquely correct, but because they happen to be compatible with the existence of observers like ourselves. Universes with different physical laws might exist, but they would not contain the stable atoms, stars, and planets necessary for the evolution of intelligent life. The anthropic principle provides a potential explanation for the apparent fine-tuning of physical constants that has long puzzled physicists. The masses of particles, the strengths of forces, and other fundamental parameters all seem to be precisely calibrated to allow the existence of complex structures and ultimately life itself. Even tiny changes in these parameters would make the universe either collapse immediately after the Big Bang or expand so rapidly that no structures could ever form. If string theory is correct, and if the multiverse contains regions with all possible physical laws, then the anthropic principle could explain this apparent fine-tuning without requiring any special design or fundamental reason. We observe a life-friendly universe simply because we could not have evolved in any other type of universe. The vast majority of possible universes in the string theory landscape would be lifeless, but observers would naturally find themselves in the rare regions where life is possible. However, many physicists find the anthropic principle deeply unsatisfying as a scientific explanation. They argue that it abandons the traditional goal of physics to find fundamental reasons for why the universe is the way it is. Instead of explaining why physical constants have their observed values, the anthropic principle simply says that they could have been different and that we happen to live in a universe where they allow our existence. The challenges facing string theory extend beyond questions of experimental verification and mathematical complexity to issues of scientific methodology and philosophy. The theory has forced physicists to reconsider fundamental questions about what constitutes a scientific theory, how theories should be tested, and what kind of explanations science should seek to provide. Some researchers have argued that string theory represents a new kind of science that operates according to different rules than traditional physics. They contend that the mathematical beauty and internal consistency of the theory provide sufficient grounds for taking it seriously, even in the absence of direct experimental verification. They point to the remarkable mathematical connections that string theory has revealed between apparently unrelated areas of physics and mathematics, as evidence that the theory is uncovering deep truths about the nature of reality. Others maintain that without experimental verification, string theory cannot be considered a successful physical theory, regardless of its mathematical elegance. They argue that history is littered with beautiful mathematical ideas that turned out to have no relevance to the physical world, and that aesthetic criteria alone are insufficient for establishing scientific truth. The debate over string theory has also highlighted the role of mathematical beauty and elegance in guiding scientific research. Throughout history, physicists have often been led to correct theories by aesthetic considerations, by the feeling that the fundamental laws of nature should be simple, elegant, and mathematically beautiful. Einstein's general relativity, Maxwell's equations of electromagnetism, and the quantum mechanical description of atomic structure all possess a mathematical beauty that many physicists find compelling. String theory certainly possesses this kind of mathematical beauty in abundance. The way it naturally incorporates gravity, unifies all the forces of nature, and connects to deep areas of mathematics strikes many researchers as too elegant and beautiful to be mere coincidence. They argue that such mathematical beauty is a reliable guide to physical truth, even when direct experimental verification is not possible. Yet beauty alone has proven to be an unreliable guide to scientific truth. History provides many examples of theories that were aesthetically appealing, but ultimately incorrect. The geocentric model of the solar system, with its complex system of epicycles and deferents, was considered beautiful and harmonious by medieval astronomers. The steady-state theory of cosmology was preferred by many scientists in the mid-20th century, partly because of its aesthetic appeal, yet it was ultimately replaced by the Big Bang model, based on observational evidence. The challenges facing string theory reflect broader questions about the nature of scientific knowledge and the limits of human understanding. As we probe deeper into the fundamental nature of reality, we inevitably encounter phenomena that lie beyond the reach of direct observation and experimentation. String theory may represent the first theory in physics that is fundamentally untestable by any conceivable experiment, forcing us to develop new criteria for evaluating scientific theories. Whether string theory ultimately proves to be correct or not, it has already transformed our understanding of the relationship between mathematics and physics, between theory and experiment, and between beauty and truth in scientific research. The challenges it presents may be forcing physics to evolve in new directions, developing new methods for exploring the deepest levels of reality that lie forever beyond the reach of direct human observation. Imagine standing at the edge of a vast ocean at twilight, watching the waves roll endlessly toward the shore. From your perspective on the beach, the ocean appears to be made of water, a continuous fluid that flows and moves according to familiar patterns. But if you could somehow shrink yourself down to the molecular level and dive beneath the surface, you would discover a completely different reality. What appeared to be smooth, continuous water would reveal itself to be made of countless individual molecules, each one dancing and vibrating in complex quantum mechanical patterns. Now imagine shrinking even further, down to the level of atoms and subatomic particles. The hydrogen and oxygen atoms that make up each water molecule would themselves dissolve into clouds of probability, with electrons existing in multiple states simultaneously until observed. Dive deeper still, and even the protons and neutrons at the hearts of atoms would reveal themselves to be composed of quarks, held together by gluons, in an intricate web of quantum field interactions. String theory suggests that this journey into the depths of reality does not end with quarks and gluons. If we could somehow probe even deeper, down to scales where space and time themselves begin to dissolve into quantum uncertainty, we would find that everything we thought was fundamental, every particle and every force, is actually composed of something even more basic, tiny vibrating strings existing in dimensions we cannot perceive. This vision represents perhaps the most radical reimagining of reality in the history of human thought. It suggests that the familiar world of objects and forces, of matter and energy, of space and time itself, might be nothing more than shadows cast by a deeper level of reality that operates according to principles completely foreign to our everyday experience. To understand what string theory tells us about the nature of reality, we must first confront one of the most profound questions in all of science. What does it mean for something to be real? When we say that an electron is real, What exactly are we claiming? We cannot see electrons directly, touch them, or hold them in our hands. We know they exist only through their effects on other things, through the tracks they leave in particle detectors, the current they create in electronic circuits, and the light they emit when they change energy levels in atoms. In a very real sense, all of modern physics deals with invisible realities that we infer from their observable effects. We believe in the existence of electromagnetic fields because we can measure their influence on charged particles. We accept the reality of quantum wave functions because their mathematical properties successfully predict the outcomes of experiments. We embrace the curved space-time of general relativity because its geometric properties explain the motion of planets and the bending of light around massive objects. String theory takes this abstraction to its logical extreme. It proposes that the ultimate constituents of reality are objects so far removed from direct observation that they might forever remain purely theoretical constructs. Yet if string theory is correct, these invisible strings would be more fundamental than anything we have ever discovered, more basic than atoms, more essential than space and time themselves. According to string theory, what we perceive as an electron is actually a particular vibrational pattern of an open string. The electron's mass, its electric charge, its spin, and all its other properties emerge from the specific way this string vibrates in the hidden dimensions of space. Change the vibrational pattern, and you get a different particle with different properties. In this view, the electron is not a thing, but rather a process, not an object, but a pattern of activity in the underlying string substrate. This process view of reality extends to everything we observe. Photons, the particles of light that illuminate our world and carry information to our eyes, are vibrational patterns of open strings. Quarks, the building blocks of protons and neutrons, are different vibrational modes of the same fundamental strings. Even the gravitons that would carry gravitational force are vibrations of closed strings looping through the higher dimensional space that surrounds us. But string theory goes even further than simply replacing particles with vibrating strings. It suggests that space and time themselves might be emergent properties that arise from more fundamental string interactions. In our everyday experience, space provides the stage upon which physical events unfold, and time provides the dimension along which these events evolve. We think of space and time as the background against which physics operates, the fixed arena within which particles move and forces act. String theory hints that this familiar picture might be completely wrong. Instead of space and time being fundamental aspects of reality, they might be like temperature and pressure in a gas, emergent properties that arise from the collective behavior of more basic constituents. Just as temperature is not a fundamental property of individual gas molecules, but rather emerges from their average kinetic energy, space and time might emerge from the complex interactions of vibrating strings in higher dimensional reality. This possibility has profound implications for our understanding of the Big Bang and the origin of the universe. In conventional cosmology, we imagine that space and time came into existence at the moment of the Big Bang, expanding from an initial singularity where all the matter and energy in the universe was compressed into an infinitely small point. But if space and time are themselves emergent properties of string interactions, then the Big Bang might not represent the absolute beginning of reality, but rather a phase transition in a more fundamental stringy substrate. The strings themselves might exist in a timeless, spaceless realm, where the familiar concepts of before and after, here and there, have no meaning. Our entire universe, with its billions of galaxies and its 14 billion-year history, might be like a bubble of emergent space-time floating in an ocean of pure, stringy potential, a temporary pattern in an eternal dance of vibrating strings. String theory also suggests that the fundamental constants of nature, the numbers that determine the masses of particles and the strengths of forces, are not truly constant at all. In our familiar four-dimensional world, these constants appear to be fixed, unchanging features of reality. The mass of an electron, the speed of light, and the strength of electromagnetic forces seem to be the same everywhere in the observable universe and at all times in its history. But according to string theory, these apparent constants are actually determined by the geometry of the compactified extra dimensions. The way these dimensions are curved and twisted determines which vibrational modes of strings are possible and what energies they possess. Change the geometry of the extra dimensions, and you change the physics of the observable world. This suggests that the fundamental constants might actually vary from place to place or change over time if the geometry of the extra dimensions evolves. Different regions of space might have slightly different values for the mass of the electron or the strength of gravity. The constants we observe might be local environmental conditions rather than universal features of reality. The implications extend to the deepest questions about the nature of physical law itself. Throughout the history of science, researchers have sought to discover the fundamental laws that govern the behavior of the universe. These laws were thought to be universal principles, the same everywhere and at all times, written into the very fabric of reality itself. String theory suggests that what we call physical laws might be more like local bylaws, rules that apply in our particular region of the universe, but that might be different elsewhere. The standard model of particle physics, with its specific particles and forces, might describe only our local cosmic neighborhood. Other regions might operate according to completely different rules, with different particles, different forces, and different possibilities for complexity and structure. This possibility connects to one of the most mysterious aspects of our universe, the apparent fine-tuning of physical constants that allows for the existence of atoms, stars, planets, and ultimately life itself. The masses of particles, the strengths of forces, and the rate of cosmic expansion all seem to be precisely calibrated to allow the universe to evolve complexity rather than collapsing immediately or expanding so rapidly that no structures could ever form. String theory offers a potential explanation for this fine-tuning through the concept of the multiverse. If string theory allows for a vast landscape of different possible universes, each with its own physical laws, determined by different compactifications of the extra dimensions, then our apparently fine-tuned universe might be just one bubble in an infinite foam of cosmic possibilities. In this view, there would be universes where the strong nuclear force is too weak to hold atomic nuclei together, leading to a cosmos filled only with hydrogen. There would be universes where electromagnetism is too strong, preventing atoms from forming molecules. There would be universes where gravity is too powerful, causing everything to collapse into black holes before stars could form. But there would also be rare universes, like ours, where all the constants happen to have values that allow for rich complexity and structure. We find ourselves in such a universe not because it is special or designed, but simply because observers like us could only evolve in universes with the right properties for complexity and life. This multiverse concept represents a radical departure from traditional scientific thinking. Instead of seeking to explain why the universe has the particular properties we observe, string theory suggests that there might be no unique explanation. Our universe might be one random possibility among an infinite number of alternatives, selected not by fundamental principles but by the anthropic requirement that it be capable of supporting observers. String theory also offers new perspectives on some of the deepest puzzles in contemporary physics and cosmology. Dark matter, the mysterious substance that makes up most of the matter in the universe, but interacts only weakly with ordinary matter, might consist of particles arising from vibrational modes of strings that have no counterpart in the standard model of particle physics. Dark energy, the even more mysterious force that is causing the expansion of the universe to accelerate, might arise from the vacuum energy of string vibrations in the compactified extra dimensions. The precise balance between matter, and dark energy that determines the overall evolution of the universe might be determined by the specific geometry of the hidden dimensions. Black holes, those enigmatic objects where gravity becomes so strong that nothing can escape, might be understood as regions where the fabric of emergent space-time breaks down and reveals the underlying stringy structure of reality. The information paradox, which asks what happens to information that falls into a black hole, might be resolved by understanding how information is encoded in string vibrations. Even consciousness itself, the phenomenon that allows us to contemplate these deep questions about reality, might ultimately be understood as a particular type of pattern in the underlying string substrate. Just as a computer program is a pattern of electrical activity that gives rise to complex behaviors, consciousness might be a pattern of string vibrations that creates the subjective experience of awareness and thought. These possibilities push the boundaries of what we traditionally consider to be physics, venturing into territory that borders on philosophy, mathematics, and even mysticism. String theory forces us to question our most basic assumptions about the nature of reality, challenging us to consider possibilities that our everyday experience tells us are impossible. Yet, for all its abstract and speculative character, string theory is grounded in rigorous mathematics and precise logical reasoning. The equations of string theory are as well defined as any in physics, and their implications follow from strict mathematical necessity rather than wishful thinking or philosophical speculation. Whether string theory ultimately proves to be correct or not, it has already transformed our understanding of what it means to do physics at the deepest level. It has shown us that reality might be far stranger and more wonderful than we ever imagined, that the familiar world of objects and forces might be just the surface appearance of something far more fundamental and mysterious. In pushing us to contemplate such radical possibilities, string theory reminds us that the universe is under no obligation to conform to our intuitions or expectations. Reality might be composed of vibrating strings in hidden dimensions, or it might be something else entirely that we have not yet imagined. But whatever the ultimate truth about the nature of reality, string theory has expanded our conception of what is possible and challenged us to think more deeply about the fundamental questions that have puzzled humanity since we first looked up at the stars and wondered what lies beneath the surface of appearances. Imagine standing at the edge of a vast, uncharted continent, knowing that beyond the horizon lie wonders and discoveries that could transform human understanding forever. The few explorers who have ventured into this mysterious territory return with tales of mathematical landscapes more beautiful than anything previously imagined, of conceptual territories where familiar landmarks like space and time dissolve into something far more fundamental and strange. This is where physics finds itself today with string theory. While the theory remains largely unproven by direct experiment, its mathematical insights have already begun to transform multiple areas of physics and mathematics, opening new pathways of investigation that extend far beyond the original goal of unifying the fundamental forces. The future implications of string theory stretch across disciplines, from the most abstract reaches of pure mathematics to the most practical applications of quantum technology. One of the most immediate impacts of string theory has been its revolutionary effect on our understanding of quantum gravity, the long-sought theory that would describe gravitational phenomena at the quantum scale. For decades, physicists struggled with the fundamental incompatibility between general relativity's smooth, continuous description of space-time and quantum mechanics' discrete, probabilistic description of matter and energy. String theory appears to resolve this ancient conflict in an elegant and natural way. The extended nature of strings, rather than point-like particles, eliminates the mathematical infinities that plagued previous attempts to quantize gravity. The theory provides a finite, mathematically consistent framework for describing gravitational interactions at the quantum level, potentially solving one of the most important unsolved problems in theoretical physics. But the implications go far beyond simply providing a quantum theory of gravity. String theory suggests that space and time themselves might be emergent properties that arise from more fundamental string interactions. This possibility opens up entirely new ways of thinking about cosmology, the study of the universe as a whole. In conventional cosmology, we imagine that the Big Bang represents the absolute beginning of space and time, the moment when the entire universe emerged from a singularity of infinite density and temperature. But if space and time are emergent properties of string dynamics, then the Big Bang might not represent the ultimate beginning, but rather a phase transition in a more fundamental stringy substrate. String cosmology suggests that our universe might have existed in some form before the Big Bang, perhaps as a contracting universe that bounced back into expansion, or as a brain world that collided with another brain in higher dimensional space. These pre-Big Bang scenarios could potentially leave observable signatures in the cosmic microwave background radiation, the afterglow of the Big Bang that still permeates the universe today. Advanced space-based telescopes and gravitational wave detectors might eventually be sensitive enough to detect these subtle signatures of string cosmology. The Planck satellite has already mapped the cosmic microwave background with unprecedented precision, revealing tiny fluctuations that encode information about the earliest moments of cosmic history. Future missions might push this observational frontier even further back in time, potentially reaching the era when stringy physics dominated the evolution of the universe. String theory also promises to revolutionize our understanding of black holes, those enigmatic objects where gravity becomes so strong that not even light can escape. Black holes have long presented fundamental puzzles for physics, particularly the information paradox, which asks what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but according to general relativity, anything that falls into a black hole is lost forever behind the event horizon. String theory suggests a resolution to this paradox through the holographic principle, the idea that all the information contained within a black hole is actually encoded on its two-dimensional surface. This holographic principle has implications that extend far beyond black hole physics. It suggests that the three-dimensional reality we observe might itself be a holographic projection of information encoded on a distant two-dimensional surface. The entire universe, with all its complexity and structure, might be like a three-dimensional movie projected from a two-dimensional screen. The mathematical techniques developed to understand this holographic duality have already found applications in other areas of physics. Condensed matter physicists use these methods to study the behavior of electrons in exotic materials. Nuclear physicists apply them to understand the strong interactions that bind quarks together in protons and neutrons. Even researchers studying quantum computing have found insights from holographic duality useful for understanding how quantum information is processed and stored. The influence of string theory on pure mathematics has been equally profound. The theory has revealed unexpected connections between apparently unrelated areas of mathematics, leading to breakthroughs in algebraic geometry, topology, and number theory. Mathematicians have used insights from string theory to solve long-standing problems that had resisted solution for decades. The relationship between mathematics and physics has always been close, but string theory has pushed this relationship to new levels of intimacy. Many of the mathematical structures that arise in string theory were originally developed by pure mathematicians, with no thought of physical applications. Conversely, physical insights from string theory have led to new mathematical theorems and techniques. This deep connection between string theory and advanced mathematics suggests that the theory might be uncovering fundamental truths about the relationship between mathematical and physical reality. Some researchers speculate that mathematics and physics might be different aspects of the same underlying structure, different ways of exploring the same fundamental patterns that govern both abstract mathematical relationships and concrete physical phenomena. The practical applications of string theory insights are only beginning to be explored. The mathematical techniques developed for string theory have already found applications in computer science, particularly in areas like optimization and machine learning. The complex geometric structures that arise in string theory compactifications are being studied for potential applications in materials science and nanotechnology. Quantum computing represents another area where string theory insights might prove valuable. The quantum mechanical properties of strings, particularly their ability to exist in superposition states and exhibit quantum entanglement, share important features with the quantum bits that form the basis of quantum computers. Understanding how information is encoded and processed in string theory might provide new insights into the design and operation of quantum computing systems. The extra dimensions predicted by string theory, while too small to access directly, might still have subtle influences on physics at scales we can observe. Precise measurements of gravitational forces at very short distances might detect deviations from Newton's inverse square law that would indicate the presence of extra dimensions. High-energy particle collisions might occasionally probe deeply enough into the structure of space-time to reveal the existence of compactified dimensions. Future particle accelerators, more powerful than anything currently existing, might eventually reach energies high enough to directly test some predictions of string theory. While the Planck scale energies where stringy effects become dominant remain far beyond any conceivable technology, lower energy signatures of string theory might still be detectable. The Large Hadron Collider has already searched for evidence of extra dimensions and supersymmetric particles predicted by many versions of string theory. While no definitive signals have been found so far, more powerful accelerators planned for the future might extend the search to higher energies and greater sensitivity. Space-based experiments offer another potential avenue for testing string theory predictions. Gravitational wave detectors like LIGO and Virgo have opened an entirely new window for observing the universe, detecting ripples in space-time created by colliding black holes and neutron stars. Future space-based gravitational wave detectors might be sensitive enough to observe the subtle modifications to gravitational waves that would result from the existence of extra dimensions. The study of cosmic rays, high-energy particles that constantly bombard Earth from space, might also provide insights into string theory physics. The most energetic cosmic rays reach energies far higher than any human-made particle accelerator, potentially probing scales where stringy effects become important. Neutrino astronomy represents another frontier, where string theory predictions might be tested. Neutrinos are ghostly particles that interact only weakly with matter, allowing them to travel vast distances through the universe without being absorbed or deflected. Future neutrino detectors might be sensitive enough to observe the subtle modifications to neutrino properties that would result from their interaction with compactified extra dimensions. The development of quantum technologies based on string theory insights might eventually lead to revolutionary new capabilities. Quantum computers based on string-inspired designs might be capable of solving certain types of problems exponentially faster than conventional computers. Quantum communication systems might achieve unprecedented levels of security by exploiting the fundamental quantum properties of string-like objects. Even more speculative possibilities involve the potential manipulation of extra dimensions themselves. If we could ever learn to access or control the compactified dimensions predicted by string theory, we might gain the ability to modify the fundamental constants of nature in localized regions of space. This could lead to technologies that seem like magic from our current perspective, such as materials with programmable properties or energy sources that tap into the vacuum fluctuations of extra-dimensional space. The long-term implications of string theory for human civilization are difficult to predict, but potentially profound. If the theory is correct, it suggests that our familiar three-dimensional world is just a tiny slice of a much larger and more complex reality. Understanding this larger reality might open up possibilities for exploration and development that we cannot currently imagine. The concept of the multiverse suggested by string theory raises profound questions about the uniqueness and significance of human existence. If there are indeed countless other universes with different physical laws, each supporting different types of complexity and possibly different forms of life, then our place in the cosmic order might be very different from what we have traditionally imagined. Yet even if string theory ultimately proves to be incorrect, its influence on the future of physics is already assured. The mathematical techniques it has developed, the conceptual frameworks it has introduced, and the questions it has raised will continue to influence physical and mathematical research for generations to come. String theory has shown us that reality might be far stranger and more wonderful than we ever imagined. It has pushed the boundaries of human thought to their limits and challenged us to think in completely new ways about the fundamental nature of existence. Whether the theory itself survives the test of experimental verification or not, the intellectual journey it has taken us on has already transformed our understanding of what is possible in physics and mathematics. The future of physics will undoubtedly be shaped by the insights and techniques that emerged from the study of string theory. The questions it has raised about the nature of space, time, matter, and force will continue to drive research, even if the specific answers it proposes turn out to be wrong. In pushing us to contemplate vibrating strings in higher dimensional space, string theory has expanded our conception of what it means to do physics and has prepared us for whatever surprises the universe might have in store for us as we continue our eternal quest to understand the deepest levels of reality. Picture a vast mountain range stretching endlessly toward the horizon, each peak representing a different attempt to understand the fundamental nature of reality. For centuries, explorers have climbed these mountains of knowledge, each generation reaching higher than the last, each new summit revealing previously hidden vistas of understanding. From the slopes where Newton first glimpsed the universal nature of gravity, to the heights where Einstein discovered the curvature of space-time, each ascent has brought humanity closer to the ultimate goal, a single, unified understanding of everything that exists. String theory represents one of the highest peaks yet attempted in this intellectual mountain range. Its mathematical elegance and promise of unification have attracted some of the most brilliant minds in physics, who have spent decades developing its intricate mathematical framework and exploring its far-reaching implications. Yet even as string theory has revealed breathtaking new vistas of understanding, it has also shown us that the summit of complete knowledge remains elusive, perhaps forever beyond our reach. The search for a theory of everything has always been driven by the deep human conviction that beneath the apparent complexity and diversity of natural phenomena lies a simple, beautiful, and unified truth. This conviction has guided physics from its earliest days, inspiring researchers to look for the hidden connections that link apparently unrelated phenomena. When Newton realized that the same force governs both falling apples and orbiting planets, he revealed a unity that had been hidden beneath the surface of everyday experience. When Maxwell showed that electricity and magnetism are two aspects of the same electromagnetic field, he demonstrated that nature's apparent diversity often conceals underlying simplicity. When Einstein unified space and time into space-time and showed that matter and energy are equivalent, he pushed the search for unity to new levels of abstraction and mathematical sophistication. The development of quantum mechanics in the early 20th century seemed at first to move physics away from unity and toward fragmentation. The quantum world revealed a reality that was fundamentally probabilistic, filled with uncertainty and paradox. Particles could exist in multiple states simultaneously. They could be connected by mysterious quantum entanglement across vast distances. They could tunnel through barriers that should have been impenetrable according to classical physics. Yet even this strange quantum world eventually yielded to the search for unification. The electromagnetic force and the weak nuclear force were successfully unified into the electroweak interaction. The strong nuclear force was understood as arising from the interactions of quarks and gluons. By the 1970s, physicists had developed the Standard Model of Particle Physics, a framework that successfully described 3 of the 4 fundamental forces within a single mathematical structure. But gravity remained stubbornly separate, refusing to fit into the quantum mechanical framework that worked so well for the other forces. Every attempt to quantize gravity led to mathematical inconsistencies and infinite results that seemed to indicate a fundamental incompatibility between general relativity and quantum mechanics. String theory emerged as the most promising attempt to bridge this gap, to find a framework that could naturally incorporate both quantum mechanics and gravity within a single unified description. The theory's early successes were remarkable. It provided a finite, mathematically consistent approach to quantum gravity. It naturally unified all 4 fundamental forces. It offered elegant explanations for the existence of multiple dimensions and the hierarchy of particle masses. Yet as string theory matured and its implications became clearer, new challenges emerged that have led some physicists to question whether it truly represents the final answer to the search for ultimate unification. The theory's landscape of possible solutions is so vast that it might be capable of explaining almost anything, potentially robbing it of predictive power. Its reliance on extra dimensions that cannot be directly observed raises questions about its connection to observable reality. These challenges have motivated physicists to explore alternative approaches to the theory of everything, each offering its own insights and facing its own obstacles. Loop quantum gravity represents one of the most developed alternatives to string theory's approach to quantum gravity. Instead of replacing particles with strings, loop quantum gravity attempts to quantize space-time itself, treating the smooth continuum of general relativity as an approximation that emerges from a more fundamental discrete structure. According to loop quantum gravity, space and time are not continuous, but rather composed of tiny, indivisible units called quantum loops. These loops weave together to form the fabric of space-time, much like individual threads combine to create a piece of cloth. At large scales, this discrete structure appears smooth and continuous, just as a photograph appears smooth from a distance, even though it is actually composed of individual pixels. Loop quantum gravity offers a very different picture of the Big Bang than either conventional cosmology or string theory. Instead of emerging from a singularity of infinite density, the universe in loop quantum gravity bounces back from a previous contracting phase when matter reaches a maximum density determined by the discrete structure of space-time. This quantum bounce could potentially eliminate the singularities that plague classical general relativity. The approach has achieved notable successes in understanding black hole physics, providing precise calculations of black hole entropy and offering insights into the information paradox. However, loop quantum gravity faces its own challenges. It has not yet successfully unified gravity with the other fundamental forces, and its predictions for observable phenomena remain limited. Emergent gravity theories represent another alternative approach that questions whether gravity is truly fundamental at all. These theories suggest that gravity might be an emergent phenomenon that arises from more basic quantum mechanical interactions, much like temperature emerges from the average motion of molecules in a gas, or pressure emerges from molecular collisions. The most developed emergent gravity theory is Eric Verlinde's entropic gravity, which proposes that gravitational attraction arises from changes in quantum information entropy when matter moves through space. According to this approach, what we interpret as gravitational force is actually the universe's tendency to maximize entropy, the measure of disorder in quantum information. Emergent gravity offers potential explanations for some puzzling astronomical observations, such as the apparent existence of dark matter and the accelerating expansion of the universe. However, the theory is still in its early stages of development and faces significant challenges in making precise, testable predictions. Causal set theory takes yet another approach to the fundamental structure of reality, proposing that space-time is composed of discrete events connected by causal relationships. Instead of the smooth manifolds of general relativity or the vibrating strings of string theory, causal set theory envisions reality as a network of discrete space-time points, each connected to others through cause and effect relationships. This approach naturally incorporates the finite speed of light and the causal structure that lies at the heart of relativity theory. It suggests that the smooth geometry of space-time emerges as an approximation when we consider the average behavior of many discrete causal events. The theory offers potential insights into the nature of time and the origin of the arrow of time that distinguishes past from future. Asymptotic safety represents a different approach to quantum gravity that attempts to make general relativity itself consistent at the quantum level, without replacing it with a fundamentally different theory. This approach suggests that gravity might have a quantum fixed point, a special regime where quantum corrections to general relativity remain finite and controllable. If asymptotic safety is correct, then general relativity might be valid at all energy scales, requiring only modifications to handle quantum effects rather than replacement by a completely different theory like string theory or loop quantum gravity. The approach has shown promising results in computer simulations, but many technical challenges remain in demonstrating its viability. M-theory represents an attempt to unify the different versions of string theory that emerged in the 1980s and 90s. These different versions, known as Type I, Type IA, Type IIB, and two heterotic string theories, initially appeared to describe different possible universes with different physical laws. However, Edward Witten's insights in the mid-1990s revealed that these apparently different theories are actually different perspectives on the same underlying 11-dimensional theory. M-theory suggests that strings themselves might not be the most fundamental objects in nature. Instead, the theory predicts the existence of higher dimensional objects called branes, short for membranes, that can have multiple spatial dimensions. Strings would be one-dimensional branes, but the theory also allows for two-dimensional membrane branes, three-dimensional volume branes, and even higher dimensional structures. Our entire observable universe might be a three-dimensional brane floating in higher dimensional space, with gravity able to propagate through the extra dimensions, while other forces remain confined to our brane. This could explain why gravity is so much weaker than the other forces. Its strength is diluted by spreading through the extra dimensions. The landscape of string theory solutions, with its vast number of possible vacuum states, has led some researchers to embrace the concept of eternal inflation and the multiverse. According to this picture, our universe is just one bubble in an infinite cosmic foam, each bubble corresponding to a different solution from the string theory landscape. Eternal inflation suggests that the universe as a whole is constantly creating new regions of space, time, each with potentially different physical laws determined by different ways of compactifying the extra dimensions. This process would continue forever, creating an infinite number of universes with every conceivable set of physical laws. While the multiverse concept offers potential explanations for the apparent fine-tuning of physical constants in our universe, it also raises profound questions about the nature of scientific explanation. If every possible universe exists somewhere in the multiverse, then what does it mean to ask why our universe has the particular properties we observe? Some physicists have responded to these challenges by developing new approaches to the theory of everything that go beyond traditional physics. Digital physics proposes that reality itself might be computational, that the universe might be a vast computer program running on some unknown computational substrate. According to digital physics, the fundamental building blocks of reality are not particles or strings or geometric structures, but rather bits of information. Physical laws would be algorithms, and the evolution of the universe would be the execution of a cosmic computer program. This approach offers potential insights into the nature of quantum mechanics and the origin of physical laws, but it faces enormous challenges in making concrete, testable predictions. Consciousness-based theories represent the most speculative approaches to fundamental physics, suggesting that consciousness itself might be a fundamental feature of reality rather than an emergent property of complex matter. These theories propose that the hard problem of consciousness, the question of how subjective experience arises from objective physical processes, might require a fundamental revision of our understanding of the relationship between mind and matter. While consciousness-based theories remain highly controversial and face significant scientific skepticism, they reflect the deep puzzles that emerge when we push our understanding of reality to its limits. The measurement problem in quantum mechanics, the hard problem of consciousness, and the fine-tuning problem in cosmology all point to gaps in our current understanding that might require radically new approaches. The search for the theory of everything has also been influenced by developments in computer science and information theory. The recognition that information is a fundamental physical quantity, not just an abstract concept, has led to new approaches that treat information processing as a basic feature of physical reality. Quantum information theory has revealed deep connections between quantum mechanics, thermodynamics, and computer science. The study of quantum entanglement has shown that information can be encoded in correlations between distant particles in ways that have no classical analog. These insights have led to new approaches to quantum gravity that treat space-time itself as an emergent property of quantum information processing. The it-from-bit hypothesis, proposed by John Wheeler, suggests that all physical entities might ultimately derive from binary choices, from answers to yes or no questions. According to this view, reality might be fundamentally informational, with matter, energy, space, and time all emerging from the processing of binary information. As we look toward the future of the search for the theory of everything, it seems likely that the ultimate answer will incorporate insights from many different approaches. String theory has revealed deep mathematical structures that connect apparently unrelated areas of physics and mathematics. Loop quantum gravity has provided insights into the discrete nature of space-time. Emergent gravity has suggested new ways of thinking about the relationship between microscopic quantum mechanics and macroscopic geometry. The theory of everything, when it is finally discovered, may not look like any of the current candidates. It might incorporate features from string theory, loop quantum gravity, emergent gravity, and approaches that have not yet been imagined. It might require mathematical tools that have not yet been developed and conceptual frameworks that push beyond the current boundaries of human thought. What seems certain is that the search itself will continue to drive physics forward, pushing us to ask deeper questions and develop more powerful tools for understanding the nature of reality. Whether the theory of everything is ultimately discovered by human scientists or remains forever beyond our reach, the journey toward that goal will continue to reveal new wonders and expand our understanding of the cosmos we inhabit. The mountain range of knowledge stretches endlessly toward the horizon, and each peak we climb reveals new summits waiting to be explored. The search for the theory of everything is not just about finding final answers, but about the eternal human quest to understand our place in the vast, mysterious, and beautiful universe that surrounds us. As our exploration of string theory draws to a close, imagine yourself once again standing beneath a vast night sky, but now with eyes that have been opened to possibilities you never could have imagined when we began this journey together. The stars that once seemed like distant points of light now appear as beacons illuminating a universe far stranger and more wonderful than our ancestors ever dreamed. Each photon that travels from those distant stars to your eyes might be the vibration of an open string, carrying its message across billions of years and countless light-years of space. The atoms in your body, forged in the nuclear furnaces of ancient stars, might themselves be intricate dances of vibrating strings, each one contributing its own unique frequency to the cosmic symphony of existence. The ground beneath your feet, which seems so solid and permanent, might be nothing more than patterns of energy oscillating in dimensions too small to perceive, dimensions that curl and twist through spaces that exist everywhere around you, yet remain forever hidden from direct observation. The very space between the stars, the emptiness that appears to contain nothing at all, might be alive with the constant vibration of fundamental strings, weaving the fabric of reality itself. We have traveled together through landscapes of thought that push the boundaries of human imagination. We have explored the possibility that everything we observe, from the smallest particle to the largest galaxy, emerges from the vibrations of objects so tiny that they make atoms seem like vast continents. We have contemplated extra dimensions that exist all around us, yet remain as inaccessible as the most distant galaxies. We have considered the idea that the forces of nature, which appear so different in our everyday experience, might be different notes played by the same cosmic instrument. String theory has shown us that the universe might be far more unified than we ever suspected. The electromagnetic force that powers our technology, the nuclear forces that bind matter together, and the gravity that keeps our feet on the ground might all be different aspects of the same underlying reality. The particles that make up matter, and the particles that carry forces between them, might be different vibrational patterns of the same fundamental strings. Yet even as string theory has revealed these breathtaking possibilities, it has also reminded us of the limits of human knowledge and the challenges that face any attempt to understand the deepest levels of reality. The scales at which strings operate are so far removed from anything we can directly observe that they may forever remain theoretical constructs, known to us only through their mathematical shadows and the insights they provide into the structure of physical law. The mathematical complexity of string theory has pushed physicists to develop new tools and techniques that have found applications far beyond their original purpose. The geometric structures discovered in studies of extra-dimensional compactification have provided insights into pure mathematics that have no immediate connection to physics. The dualities revealed by string theory have shown unexpected relationships between apparently different areas of science and mathematics. Perhaps most importantly, string theory has forced us to confront fundamental questions about the nature of scientific knowledge itself. What does it mean to understand something that can never be directly observed? How do we test theories that make predictions about realms far beyond the reach of any conceivable experiment? What role should mathematical beauty and elegance play in guiding our search for truth about the natural world? These questions have no easy answers, and they reflect broader challenges that science faces as it probes ever deeper into the fundamental nature of reality. As we push toward the limits of what can be known, we inevitably encounter phenomena that challenge our traditional methods of investigation and force us to develop new approaches to understanding. String theory represents one response to these challenges, an attempt to use mathematical consistency and aesthetic criteria to guide us toward truth, even when direct experimental verification is impossible. Whether this approach ultimately succeeds or fails, it has already expanded our conception of what it means to do science and has prepared us for the possibility that some aspects of reality might forever remain beyond the reach of direct human observation. The journey we have taken together through the landscape of string theory also reflects a deeper human story, the eternal quest to understand our place in the cosmos and to find meaning and connection in what might otherwise seem like a chaotic and incomprehensible universe. From the ancient Greeks who first proposed that all matter might be composed of indivisible atoms to the modern physicists who study vibrating strings in higher dimensional space, humans have always sought to find the simple principles that underlie apparent complexity. This quest has driven some of the greatest achievements in human history. It has led to technologies that have transformed civilization and to insights that have fundamentally changed our understanding of our place in the cosmic order. It has shown us that we live in a universe governed by mathematical laws that can be discovered through careful observation and rigorous reasoning. String theory continues this grand tradition, pushing the boundaries of human thought to their absolute limits and challenging us to consider possibilities that defy our everyday experience and intuition. Whether the theory ultimately proves to be correct, or simply another stepping stone on the path toward deeper understanding, it has already enriched our conception of what is possible and has reminded us that reality is far stranger and more wonderful than we ever imagined. The story of string theory is also a reminder that science is fundamentally a human endeavor, driven by curiosity, creativity, and the deep desire to understand. Behind every equation and every mathematical insight are real people who have dedicated their lives to pushing the boundaries of knowledge, often working for decades on problems that may never be fully solved within their lifetimes. These researchers continue their work not because they are certain of success, but because the quest itself is meaningful and valuable. Each new mathematical insight, each unexpected connection between different areas of physics, each glimpse of deeper unity beneath apparent diversity, contributes to the ongoing human effort to understand the universe we inhabit. As we conclude our exploration of string theory, we should remember that this is not the end of the story, but rather a pause in an ongoing narrative that stretches back to the earliest human attempts to understand the natural world and forward to discoveries we cannot yet imagine. The questions that string theory has raised about the nature of space, time, matter, and force will continue to drive research for generations to come. Future physicists will build upon the insights and techniques developed by string theorists, whether they ultimately confirm the theory's predictions or move beyond it to develop even more comprehensive frameworks for understanding reality. The mathematical tools created for string theory will find new applications in areas we cannot currently foresee. The conceptual frameworks it has introduced will influence how we think about fundamental questions in physics and mathematics. The children who are just beginning to learn about science today may grow up to make discoveries that will revolutionize our understanding of the universe in ways we cannot currently imagine. They may develop new experimental techniques that allow us to probe the Planck scale directly, or they may discover entirely new theoretical frameworks that make string theory seem like a simple approximation to a deeper truth. What we can be certain of is that the human desire to understand will continue to drive us forward, pushing us to ask deeper questions and to seek ever more comprehensive answers. We will continue to climb the mountain of knowledge, knowing that each summit we reach reveals new peaks stretching endlessly toward the horizon. The universe has kept its secrets for billions of years, slowly revealing them to curious minds, willing to ask difficult questions and to follow the evidence wherever it leads. Whether those secrets ultimately include vibrating strings in extra dimensions or something else entirely that we have not yet imagined, the search itself represents one of the highest expressions of human creativity and intelligence. As you return to your daily life after this journey through the landscape of string theory, carry with you a sense of wonder at the mystery and beauty that surrounds us at every moment. Remember that beneath the familiar surface of everyday experience lies a reality far richer and more complex than most people ever suspect. The atoms in your body, the light that illuminates your world, the forces that hold everything together, all participate in a cosmic dance of extraordinary elegance and beauty. Whether that dance is ultimately choreographed by vibrating strings or by principles we have not yet discovered, it connects you to the deepest levels of reality and to the ongoing human quest to understand the universe we call home. In contemplating these possibilities, you participate in the same spirit of inquiry that has driven human progress for millennia and that will continue to illuminate new pathways toward understanding, as long as there are minds capable of wonder and hearts brave enough to seek truth in the face of mystery. The journey toward understanding is endless, and every step brings us closer to appreciating the profound beauty and mystery of existence itself. In this eternal quest, we find not only knowledge but also meaning, connection, and a deeper appreciation for the magnificent universe that has given rise to minds capable of contemplating their own existence and seeking to understand the fundamental nature of all that is.